Good morning guys, I hope you are well. Welcome to another video for Ahmad Science UK. This video is all about the development of the atom. Now as always, please follow on social media channels, like and subscribe on YouTube first, press that button, and then follow on social media channels, Ahmad Science UK for the Facebook page, and then at Ahmad Science UK for Instagram. So what we're going to look at in today's lesson is part 2 of development of the model of the atom. Now, if I said it in the last video as well, but I'm going to say it again, it doesn't matter which order you watch part 1 and part 2 in. Some people prefer to have the big picture and then look at the specifics, whereas some people like to look at the specifics and then build up a big picture, whichever way you prefer. In the last video I looked at how new scientific evidence changes the models we use and describing the stages of the development of the atom. Today what we're going to look at is specifically what evidence led to the changes in the atomic model and describing the difference between plum pudding and the nuclear model of the atom, right? So, first thing I want you to do is what would happen, or think about, is what would happen if you kicked a football at a curtain that was covering something that was unknown. So, say for example, when you kick this football at this curtain, which is covering something that we don't know, one of 3 things is most likely going to happen. First of all, what could possibly happen is the ball hits the curtain and then it falls down. Now, that means that whatever's behind the curtain is absorbing the energy of the football that's being kicked, so it could be some padding or whatever it might be. Second situation is the ball is kicked at the wall or at the curtain, and then when it hits the wall, it's going to bounce back. So clearly in this particular situation, you've got something very hard and very solid behind the wall that's kind of bouncing, providing enough support, enough force, so that when the ball hits it, it will bounce back towards whoever the person is that's kicking it. And then the third situation is that the ball could hit the wall and it will go through the curtain. So whatever's behind the curtain, could be nothing, will end up, the ball will go through the curtain and you know, go from there. Now, what would be really strange is if I said, right, there's a football there and I'm going to kick it and there's a solid brick wall behind it, and the ball, rather than bounce back, decides to go through, which is really strange. And that's kind of partly the thinking behind why the model of the atom had to change, and this was all related to the alpha scattering experiment. But let's take a step back. Let's understand what's exactly happened. So in the last video I talked about J.J. Thomson, and he discovered the electron. So when we talk about the change from Dalton's model to J.J. Thomson's model, the key difference was the discovery of the electron, and therefore what you ended up having was this positive kind of ball, positive spherical marble almost, which had electrons embedded in it, and this was called the plum pudding model. The model suggested that the atom itself was positive, with negative electrons embedded in it. So overall, in terms of the charge of this particular atom, it was neutral. And that we know is true of atoms. Atoms in when they're not ions are neutral, right? They've got the same number of, and according to a current model, they've got the same number of protons as electrons. And that's kind of the evidence, and that was the understanding at the time. However, what happened was Ernest Rutherford carried out the alpha particle scattering experiment. Now in this, what he did was he set up an alpha source, so he used radium, and he fired alpha particles at a very, very, very thin piece of gold foil. So in theory it was meant to be a few atoms thick. And when he fired this, if you've got the plum pudding model, what you should expect is all the alpha particles just go straight through to the other side. Yeah, it's like the equivalent of firing a bullet at a birthday cake. Most of the bullets are going to go straight through the birthday cake. All of the bullets are going to go straight through the birthday cake. But in this experiment, there was a couple of results that really threw off the findings and the understanding of the plum pudding model. Because if you've got a plum pudding model and you fired a very small alpha particle at it, the last thing you'd expect to do is that particle to bounce back. That particle to bounce back is like the equivalent of firing a bullet at a birthday cake and one of those bullets ricocheting and coming back towards you. It wouldn't happen. But what they observed was that some particles, very few, were deflected through large angles. And very, very, very few, one in almost 2,000, actually were deflected by more than 90 degrees. So they bounced back off whatever was in this gold foil. And that really confused the model, the plum pudding model, as it currently stood. So, well, let me clear the ink. You don't need to write this bit down because it's not in a white box with a blue border, but that's just for your understanding. During the experiment, most of the alpha particles went straight through, so that was pretty much what was expected to happen. However, there were some particles that were deflected through large angles, and even fewer particles, but they were there and they were continuously there, that were deflected by more than 90 degrees. In other words, that's 0, that's 90, that's more than 90 degrees. Yeah? And so some of them were deflected back. Now, what that meant was that caused issues with the plum pudding model as it currently stood. So the results from the alpha scattering experiment led to the conclusion that most of this mass of an atom was actually concentrated inside something very small. So they refer to it as a nucleus, and the nucleus was charged positively. This model replaced the plum pudding model. So what you ended up with was a situation where you've gone from having a very big mass, or rather the mass spread out over the whole of the atom, to a situation where you've got most of the mass concentrated in this nucleus. Yeah, notice how the electrons are still all on just one shell. They're all just going around the outside of this nucleus. Then came along Niels Bohr, and Niels Bohr suggested that electrons actually, when they are orbiting an atom, they have specific energies, and we can measure this currently. And you see these all the time when you see neon signs. They give out specific electromagnetic wavelengths when they de-excite and they drop down to an energy level. Point being is that Neil worked out that electrons orbited at specific energies around the nucleus, and that energy meant that we moved from a model where you've got all the electrons just orbiting around the outside to having specific shells around the atom. So Niels Bohr's experiments with hydrogen in particular kind of led to this particular discovery. And then when they did later experiments, this led to the idea that the positive charge itself in the nucleus actually could be subdivided into smaller particles, and all those particles always seem to have the same amount of charge. And therefore what they did was they referred to those particles as protons, and that was the name given to them. So we went from a model where all the mass was concentrated in the middle to actually having a positive mass all concentrated in the middle still, but that mass being made up of smaller individual particles called protons, right? So far we've gone from having spherical balls to having the plum pudding model to having a nuclear model to having energy shells and then having protons. So the only thing missing from this were the neutrons, and this was discovered by James Chadwick, who provided the evidence to show that neutrons existed within the nucleus. Now, the neutrons were discovered, it wasn't until for a while, it was about 20 years odd, until neutrons were discovered, and that's because neutrons don't have a charge, so they're not as easily detected as, say, protons or electrons can be. And kind of the key thing that you're going to have to do in your exams, or one of the things that you might be asked to do, is compare the plum pudding model to the nuclear model, okay, and kind of link the evidence to what it was that led to this change in the models, which was, in terms of kind of visually, it was the most significant. So the differences between the plum pudding model and the nuclear model are that for the nuclear model, most of the mass is concentrated in the nucleus. And the reason why they say this is because of the particles that deflected more than 90 degrees. More than 90 degrees. Because if you're firing something at, say for example, I threw a piece of paper and it hit me, it's very unlikely that the paper, I'm going to move back and the paper's going to kind of stay where it is, or the paper's going to go through me, as it were. So the mass of the nucleus needed to be a lot bigger than the alpha particles that were hitting it in order to make sure that the alpha particles deflected backwards towards the source that was firing it. Second thing was that most of the atom is empty space, because as we saw from the results, most of the particles, most of the alpha particles just went straight through. So if they're not close to the nucleus, then what's going to happen is the alpha particles are just going to carry on straight through, not really affected by anything, and that's it. And the nucleus is positive rather than the whole atom. So one of the big things is if you've got an alpha particle, and alpha particles they knew were positive, they could measure that. If an alpha particle which is positive is going to come close to the nucleus, not head on, but close to the nucleus, what's probably going to happen is it's going to be deflected in a very large angle. The reason being is opposites attract and like charges repel. So if you've got a positive alpha particle and you've got a positive nucleus and they come close to each other, what's going to happen is one of them, whichever one's smaller, is probably going to move off and be repelled in a particular direction. Yeah. And those were the three key discoveries, and each one of the results, or each one of the alpha particles that I showed you in the diagram at the beginning, linked to kind of one of the changes. So most of the empty space is most of the particles went through. Can't spell when. And in terms of the nucleus being positive, this was related to alpha particles being deflected through large angles. And obviously those angles have to be less than 90 degrees. Yeah? Right, guys. That's a quick summary of kind of the development of the model of the atom, with more specific details and the comparison of plum pudding model and the nuclear model. If you found them useful, then always like and subscribe, and follow on the social media channels. Thank you very much. Take care, look after yourselves, and be safe. Bye.